Hi, welcome back to this 7th video on partial differential equations. This is problem 8.8 in Mathews and Walker, and it's kind of a cute problem. Without the hint, I think it would be a lot more difficult. So let's dive in there. The problem says, find the lowest frequency of a drum head in the shape of an isosceles right triangle with sides A, and A times the square root of 2. Hint, consider the modes of a square drum. So what we have is we have an isosceles right triangle. A, this is the square root of 2 times A. And the boundary conditions, the wave equation is del squared U is equal to 1 over c squared. C is the speed of the wave. The second partial u with respect to t2. And we've separated this many times before. I'm just going to immediately do this time separation. U of x comma t. And this is a two-dimensional problem. Whatever exists in the third dimension is irrelevant. Times e to the minus I omega t. You could put sine omega t there, cosine omega t there, whatever you like. So substituting this into the wave equation gives us the Helmholtz equation. Del squared u plus k squared u equals 0. K equal to omega over c. Okay, now the problem says extended to a square drum. So that seems like that makes sense. So let's extend this to a square drum like this. Oh, and the boundary condition I forgot to state. Is that u equals 0 on the boundary of the right triangle. Put that for right triangle. So let's extend it to a square like this, AA. And let's put coordinate axes. We're going to use rectangular coordinate axes. No spherical or cylindrical this problem. So this is the x-axis. This is the y-axis. And what we know is that u is 0 here. It's 0 there. It's also 0 right here on the diagonal. So now we should do some thinking. And the basic idea is that we could see that there's a symmetry here. Let's say we flip in this diagonal. The first question you should think about is, what can the derivative, we know that u is 0 on the diagonal, what can the derivative be on the diagonal? Let's say the normal derivative. Well, we know from a second order differential equation that if u equals 0 and u prime equals 0, then our solution is simply u equals 0. In the whole region, u equals 0 will satisfy that. Basically, you know, once you start out at 0, since I'll do the 1D case, which we've done. The 1D case, if you have a function here which is 0, if f equals 0 and f prime equals 0, and f satisfies some kind of second order DE, then f is equal to 0, you know, everywhere. And the reason is f equals 0 will satisfy this boundary condition and the differential equation if it's a linear equation like second order like this. So we can't have f prime equals 0 on the boundary. Now, so you can imagine we have like a square like this. So if the derivative is, let's say, positive here, it's got to be continuous throughout the whole thing. If it wasn't continuous, you know, we don't want it to be where it like it's going down from this way and then up this way, because then it's not continuous in the whole square region. We want a continuous solution. So the answer is, and since we want u equals 0, we should take u is anti-symmetric across the diagonal. So if u is positive in this way, you could think of the drum as going up a little bit. Then on the other side, it's going to be down a little bit and everything. It can't be up on both sides, because then it comes to a crest there, and that's no good. So let's write our solutions. It's pretty easy to solve this. It's just, by the way, I didn't write it down, but del squared u in rectangular coordinates is simply the second partial u with respect to x plus the second partial u with respect to y. Okay. So to solve this equation, it's going to be fairly easy. You know, it's when we take two derivatives of a trigonometric function, we get the negative, and that's exactly what we want here. So you can just write down, call it an ansatz, or just call it an obvious solution. It's going to be the sum. I'm going to label indices. Nx is the x indices, ny is the y indices, rather than using n and m. And it's some coefficient, which depends on nx and ny. There's going to be sine pi nx x over a, sine pi ny y over a. Now let's first check that this solves the boundary conditions. If x equals 0, over here it's 0 because the sine of 0 is 0. If y equals 0, it satisfies it. Now if x equal a, the sine of pi times an integer, I should have said nx, y, integers. Actually, they're positive integers. If they're 0, you just have a 0 solution, which is meaningless. And if they're negative, the sign of it's not an independent solution. The sign of minus x is the same as minus the sign of x. So basically, we can restrict ourselves here to, and we could put the negative in the coefficient. We can restrict ourselves here to positive integers. Now, so if x equal a, on this boundary it's 0, and if y equal a, on this boundary it's 0. So this solves, we're solving this Laplace equation in the square boundary, and by requiring it to be anisymmetric across the diagonal, it's going to have to be 0 on the diagonal, and so we'll satisfy the original problem. That's the aim. Now if you substitute this into the Helmholtz equation, you get the obvious pi squared over a squared nx squared plus ny squared equal k squared equal omega squared over c squared. So we will, our goal is to find out what nx and ny are, and to find the smallest ones, and that will give us the lowest frequency. So probably the hardest part of this problem, for me at least, was, it took a few moments thought, was flipping across the diagonal. What's the transformation? Where does x, y go to? And the answer is pretty obvious. I don't know why it took me a few seconds, but okay. Let's just verify it. The point 0, 0 goes to AA. That's good. 0, 0, AA. The point 0A goes to, so the point 0A is this point, and that will go to 0. Sorry, let's say if x equals 0, 0, 0 goes to AA. That's good. Now let's do x equals 0, y equal a. That will go to, it's not what I want. Maybe I wrote this down wrong. Let me think about this for a second. Maybe it's a minus x and a minus y. Zero a. Okay, I got it right. I'm sorry. This is why I was confused when I did this. So 0a goes to 0a. When you flip across the diagonal, this point doesn't move, and this point doesn't move. A0 goes to A0. A minus y is A minus x is 0. So these 2 points don't move. And then the one that we better get right is AA. And AA obviously goes to 0, 0. So this point goes here. That point goes there. These 2 points don't stay the same. That's our flipping. So now what we want to do is we want to substitute the value of the amplitude of the vibration, u of xy. When we look at it in the symmetry across the diagonal, it goes to u of a minus y, a minus x, and we want that to be equal to negative what we started out with. That's what we mean by saying it's anti-symmetric. So this is the condition that we have to verify. Well, we have to use this condition and find the what that tells us. So this is not too hard. Let's do it. U of a minus y, a minus x is equal to the sum of nx, the sum over ny, anx, ny, sine pi nx a minus y, because we're using a minus y for x now, over a sine pi ny a minus x over a. Okay. Now this is equal to the sum over nx ny, a nx ny, negative 1 to the nx minus 1. So let's figure out where that comes from. Okay, if I divide by what I have is I have a sine. When I divide by a, I get pi nx minus pi nxy over a. Now if you remember your trig identities, the sine of this is going to be the sine of that, but that's 0, so I don't care about that. Then it's going to be the cosine of that times the sine of that. Okay, the sine of this is just negative the sine of n sine pi nxy over a, and we have a negative sign. And the cosine of pi nx, the cosine of an integral multiple of pi, is negative 1 to the nx. And I subtracted 1 to take care of that other minus sign. And the other one is exactly the same. Negative 1 to the ny minus 1 sine pi nyx over a. Okay. Now, I'm going to do a trick that physics people do all the time. Let's just rename our indices. Nothing prevents us from renaming our indices since we're summing over all of them. So let's do this renaming of indices. So now it becomes the sum over nx, ny, a, ny, nx, negative 1. When we combine these two terms, there's a negative 1 twice from each minus 1, so that's a 1. Then it's just a negative 1 to the nx plus ny. And switching those, renaming them doesn't do anything. Then I have sine pi nyy over a sine pi nx x over a. And this whole thing should be equal to minus u. So this, I'll put a question mark. This is what we need to get. The sum over nx, ny, anx, any, sine pi nx x over a, sine pi ny y over a. Okay, so this is equal, no problem. By the way, it's supposed to be equal to minus that. It's supposed to be equal to minus u. That's equal, that's good. This is equal, that's good. So we end up getting the equation. We can satisfy this if we have a ny nx equals times minus 1 to the nx plus ny, if that is equal to minus anx ny. This is our condition on the coefficients. Okay, now the first thing when we look at this is that we have to have nx unequal to ny. Because if nx is equal to ny, then this is, whatever this is, it's going to be 2nx, it's going to be negative 1 squared, so that's going to be 1. And we're going to have a something something where the somethings are the same. We're going to have, if nx equal ny equal, let's say m, then we're going to have m equals minus m. That can only happen when m equals 0. So we can't have any time the coefficients are equal in the matrix of coefficients, we're going to have 0. Now, let's just do the two cases. If nx and ny have opposite parity, and parity means even or odd. So if one is even and the other one is odd, then this is going to be an odd number. An even plus an odd number is odd. This is going to be a minus sign. And so then they're equal. So that implies when they're of opposite parity, this implies a ny nx equal to a nx ny. If they have the same parity, and that implies that a ny nx equal minus a nx ny. Okay. So this is sort of our solution. Any solution which satisfies this requirement is good. And we'll get the lowest frequency in a second. What I want to verify, let's verify that we satisfy boundary condition on the diagonal. I mean, if we didn't make a mistake, it should be okay. So the diagonal, the equation for the diagonal is simple. X plus y equals a. Again, when this point has x equals 0, y equal a, so that adds up to a, and this point has x equal a, y equals 0, that adds up to a. So our solution is going to be the sum of nx, ny, anx, ny, sine pi nx x over a, sine pi ny y. Oops, Okay, so for y, I'm going to substitute a minus x over a. This is equal to the sum over nx and y, anx and y, sine pi nxx over a. Then I'm going to get, doing the same thing we did over there, I'm going to get -1 to the ny minus 1 sine pi ny x over a. This is equal to the sum. Now I'm going to start combining terms. I'm going to sum over those terms where nx is less than ny, nx is unequal to ny, and they have the same parity. And then below it, I'm going to add the same thing again. Sum nx less than ny, and x unequal to ny. Well, that obviously follows from that. The sum over opposite parity. So now what am I going to get here? I'm going to get a nx and y so if I have like ny is the greater one, that will be one term, but the other term would be nx is the greater one. So that term would be a ny nx. So if nx is smaller, let's say we have 1, 3, we're going to have 1, 3 here. But the 3, 1 term, when we get the reverse term, it won't occur, will only occur the other way. Okay. Times the sine pi nx x over a sine pi ny x over a -1 to the ny minus 1. Okay. Now this is equal to 0 because when they have the same parity, we said that they have opposite coefficients. So that equals 0. That takes care of that term. Now down here we have the same thing. A nx ny plus a ny nx sine pi nx x over a sine pi ny x over a. And here I have -1 to the ny minus 1. That corresponds to this term. I have plus -1 to the nx minus 1. That corresponds to that term. Now, because they have opposite parity, these two are opposite and this equals 0 due to opposite parity. Okay, so that verifies that we satisfy on the boundary. Now going back to the original problem, we have to get the lowest frequency, and the lowest frequency will correspond to nx equal 1 ny equal 2, or ny equal 1, nx equal 2. And the Eigen Function is sine pi x over a, sine 2 pi y over a, plus sine 2 pi x over a, sine pi y over a. And in terms of this thing, it's just pi squared a squared times 2 squared plus 1 squared is equal to omega squared over c squared. So it's very simply as omega is equal to pi square root of 5 c over a. That's our lowest frequency. So there's nothing really difficult in this problem, but you can, if you're like me and discrete mathematics is not your strong point, you can get confused on these transformations or on these summations here and how you get them all. Basically, we separate them into same parity and opposite parity, and then we separate them into where nx is smaller than ny and nx is larger than ny, and I just rewrote it this way for the term the other way. And same thing here's on opposite parity. So it's a nice little problem, and sometimes in symmetries, if you see something like a shape like this, a right triangle, you know, it's not easy to solve. It's not trivial to solve, but if you think rectangular coordinates and extending it to a square and then thinking what happens on the boundary, all of a sudden it becomes an easy problem. Okay, this will end my videos on separation of variables. There are a lot more problems. I think there are a total of 41 problems in Mathews and Walker on Chapter 8, and they discuss a lot more techniques, including transform techniques, Wiener-Hoff, and some other special things. So at some point in time, and Green's functions in the next chapter as well. So at some point in time, I may get around to making some videos on these. Thank you very much.